So good evening, everyone. Welcome to Science at the Theater's Dark Secrets, what science tells us about the hidden universe, sponsored by the Friends of Berkeley Lab and co-sponsored by the Lawrence Hall of Science. My name is Jeff Miller, and I'm head of public affairs. Berkeley Lab, of course, is known for its energy research. Tonight, though, we will not be talking about biofuels as we did last month. Instead, we will be discussing all things cosmological, including a different kind of power source called dark energy. Our expert guides for this trip through the universe tonight have not had to travel too far, thankfully. They are Berkeley Lab scientists Alexei Leoto, David Schlegel, and Saul Perlmutter, together with our moderator John Fowler, health and science editor at KTVU Channel 2. We are going to try to get you excited about all that we know and all that we don't know about the universe. Our program will consist of presentations and conversations for approximately 1 hour that will be followed by 30 minutes for your questions. Microphones are located here on this level and also in the mezzanine above, so everyone gets a chance. Please keep your questions short and your hypotheses about the future and fate of the universe shorter still. We want everyone who has a question to get a chance to ask it. If we run out of time, you can email your question to friendsofberkeleylab@lbl.gov. That's friendsofberkeleylab@lbl.gov, and we'll try to get it answered for you. Tomorrow on the News Center link on the Berkeley Lab website, which is found at lbl.gov, we will be posting a new 3-part series on dark energy with the next level of detail about all of the projects you will hear about this evening. And following the question and answer period, weather permitting, some of you saw that we have telescopes set up outside. These will be there for your sidewalk stargazing, again, if weather permits. And I hear that Jupiter and the moon are going to be prime attractions this evening, again, if we can see them. The telescopes are courtesy of the Lawrence Hall of Science and the International Year of Astronomy. That's the Galileoscope that you see out there. Before you leave, we also would like you to fill out the audience surveys, which were handed out at the door. They help us plan future programs. Lastly, those of you who are here for the first time, I'd like you to please raise your hand so we can see how effective our advertising was. Excellent, excellent, excellent. Thank you all for coming. John, the stage is yours.
Thank you, Jeff. It's very gratifying to see so many people here tonight. This is going to be something I think you will remember. I've had the opportunity for the last few minutes to talk with these 3 distinguished scientists. They all are brilliant, and they all have wonderful, fun, and engaging things to say. We're very fortunate to be here in Berkeley. The Lawrence Berkeley National Lab has some of the most preeminent scientists in the world. Some of the best minds are sitting to my right. I want you to, tonight, put aside your fears of the H1N1 flu. Don't worry about health care reform. And for a moment, put mortgage crises on the back burner. Open your minds and be prepared to have your minds stretched. Some would say spaghettified. This is probably the most remarkable evening you will have had, at least in recent memory, I can guarantee you. And I'd like to start with Dr. Saul Perlmutter on my right, who will begin our journey through the cosmos.
So I was asked to begin with a little bit of an introduction for the few of you who don't already know what we're talking about. I figure most of you by now have become experts in all this field. But for those who aren't, I thought I'd walk through a little bit of what got us to this particular point in our research today, and I think a little bit why we feel so lucky to be able to work on the topics that the 3 of us and our colleagues are all working on. So I was going to begin by just pointing out that the sorts of questions that we're working with here are ones that go back to prehistory. I imagine the very first human beings would look up at the stars at night and find themselves wondering what sort of world we live in. Does it go on forever? Will it last forever? And it turns out that we didn't really make a huge amount of progress beyond asking philosophers until just this past century, when Einstein gave us some conceptual framework to think about this in his theory of general relativity. And he set out a way of writing down equations that describe the universe. He ended up having a problem, though, when he did that, which is that he could get a universe that would contract, and he could get a universe that would expand, but he couldn't get one that would just sit still. And he, as far as he knew, that's the universe that he saw around him and that his astronomer friends told him that we lived in. And so he ended up having to put a fudge factor into his equation. He made it sound good. He used the Greek letter lambda. He called it the cosmological constant. But it was just an attempt to make the whole thing work. And he famously regretted it just a dozen years later when Edwin Hubble went out and discovered that really the universe is expanding. And he kicked himself, and he said it was his greatest blunder having put that in. I've been kidding with people saying that he could have predicted that the universe was expanding. He could have been famous, but he didn't. And so what it was that Edwin Hubble was seeing when he looked through his telescopes was the special features of very distant galaxies. Now, he didn't know they were galaxies at the time. They were these fuzzy nebulous regions in distant space, and they were called nebula. But he discovered that the ones that were further away were moving faster away from us, and this was the hallmark of an expanding universe. Now, the whole idea of an expanding universe is, to me, just a mind-boggling thought. And I think that when you work with cosmology, one of the real pleasures of it, I think for many of us, is the fact that you get to work with completely mind-boggling concepts and just treat them as if they were day-to-day working hypotheses. But I thought that since I'm describing and we'll all be talking about a universe that's expanding, I should say a word about what we mean, because it's pretty clear what we cannot mean. It cannot be that we're talking about something that's sort of exploding from a point out into space. That doesn't make any sense because the space that it's exploding into would be universe. And so that's not what we mean when we say the universe is expanding. I was trying to come up with a way of capturing this in a somewhat simplified drawing. So this is my rather simplified universe. It's all right, very simple. You're supposed to imagine that these dots here are galaxies, and you're supposed to imagine that this is an infinite universe that goes on forever, up and across and into the board and out towards you. And the only thing about it that's important in this particular model is that there's a characteristic distance between every galaxy. And so then when we say that the universe is expanding, all we really mean is that in this infinite universe with galaxies spread out throughout the universe, that average distance between the galaxies just gets a little bit bigger. And that's the entire dramatic effect of an expanding universe. But it seems like a fairly simple idea, but as soon as you start thinking about a universe that's expanding like that, it starts giving you other ideas that you can now bring to bear on your original question of what's going to happen in the future of the universe, because you start wondering, well, if it's expanding now, is that going to go on forever? And what happens if someday it starts contracting? And will the universe come to an end? And the way that you can you can address that kind of question is to go back and look in history to see, well, what has it been doing? Has the expansion been changing in the past? And it turns out that that was something that we could set out to do now it's 20 years ago, taking advantage of an object out there in the universe, or objects that are stars that explode. And a distant star, when it explodes, is a very dramatic event because that one star can be as bright at its brightest as all of the 10, 100 billion stars in that galaxy in which that one star was found. So that's a pretty dramatic event, and you can use it to see vast distances across the universe. Now, the nice thing about looking back at great distances across the universe is that, now it won't stop. There it goes. Is that we can take advantage of the fact that the light is taking time to travel. So when you're looking very, very far away, you're looking at events that happened very, very far back in time. And since what we wanted to do was study the history of the expansion in order to predict its future, that's very convenient. We get to look at the history by looking at things that are far away. Now, how far away that is and how far back in time you're looking is kind of interesting to think about, because the sun isn't that far away. The light's traveling to us for some 8 minutes, so it's it's reasonably close. Near a star, we orbit around our sun 4 times. 4 years go by since the light left that star. But it starts becoming interesting as you start looking at the nearest galaxy of stars, because now you're looking at light that left those stars in that nearest galaxy some 150,000 years ago. So that's going to be an appreciable amount of time. That's about the time where here on Earth we see the first evidence of human culture artifacts. That's my attempt at human culture. The nearest grouping of galaxies, so the nearest cluster of galaxies, is even further away. Now you're looking about some 65 million years back in time. So light leaving those stars left there around the time we're here on Earth, the dinosaurs were going extinct. And it's even more dramatic when you ask, much more dramatic when you ask, how far away can you really see? And some of the most distant stars that explode, these supernovae that we've actually been able to discover and see, you're actually looking back some 10 billion years into the past. And that's some 2/3 of the way back to what we think was the beginning of the universe as we know it. So to give you a sort of feel for that, there's a movie that I've modern day nearest star, right? There's a movie that I think is I like that sort of captures some of the sense of this. And probably the lights will come down a little bit when we do this. It begins with an artist's conception of a supernova going off in this distant galaxy, but then it morphs onto actual real data. So there's the supernova right there. Real data that was collected with first the Hubble Space Telescope that you see here, and then pulling back, actually if we can turn the lights down a little bit, pulling back, you can see that this is morphed onto data from many, many telescopes, and you get a sense that we're looking very, 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 it just goes on forever. It's very, very, very far away, and there's the sense of where you're seeing it in the sky. So these are tremendous distances that you're getting to look at, and that's, that particular case was a supernova that exploded some 10 billion years ago. Now, that means that you're able to study events that occurred several billion years, going from several billion years all the way back to 10 billion years back in time, if you can find a number of different supernova. And that's something that we set out to do now it's 20 years back, and it took a while to develop the technique. And you want to take advantage of one other aspect, two aspects of this. One is that there's a kind of supernova that you can recognize by its spectrum, which is always the same brightness. And so if you measure how bright it is at peak, you can tell how far away it is, just like you could tell how far away a candle was, so we call a standard candle, as you walked across the room or down the block with a candle. You could tell how far away it was by how bright it looked if you knew how bright they were when held nearby. And so the supernovae easily give us that information. They tell us how far away it is, and hence how far back in time you're looking, because you know the speed of light, as I mentioned. They also give you one other piece of information, which is you can use the color of the supernova to tell you how much the universe has stretched, because the supernova looks blue when it explodes, and that's a short wavelength. And then while the universe stretches, the photons travel to us from the very distant universe, and their wavelengths stretch just with the universe. So that means that by the time it reaches us, it looks red. That's called redshift. And exactly how red it looks tells you how much the universe has stretched since the time of that particular supernova explosion. So it turns out that if you can find a number of these supernovae, and we ended up using some of the largest telescopes in the world to do this over a number of years, you can map out for each supernova telling you how far back in time it exploded, and you can find out how much the universe has stretched since that time. You do that, let's say, for a supernova 2 billion years back, 4 billion years, another supernova 6 billion years, and you can follow the history of the expansion and learn. Now, it turns out that was a lot of work. You had to find these supernovae exploding in these very distant galaxies. Each of these little faint blue things is a distant galaxy. Some of these are about 4 billion years back. And you're looking in all of them to see if you can find one spot that gets bright for supernova to explode. And so a lot of the work involves developing the computer software to be able to track that down. And eventually we developed the capabilities of having the supernova point out that one event amidst all the field of galaxies where the object looks brighter 3 weeks later than it did 3 weeks earlier, and the difference is the supernova. And of course, it's helpful to do this in space as well. From the Hubble Space Telescope, you get to see just the spot that's a supernova on top of the galaxy. Now, that meant that after, what was supposed to be a 3-year project, 10 years later, we actually had enough supernovae to do this measurement, and we were ready to look at the plot of the average distance between galaxies as a function of time and see what the fate of the universe could be. And there were just a few options. One was that the universe was going to be slowing because all the gravity in the universe would slow the expansion, but it would just keep expanding forever. And to give you a visualization of what that looks like, this animation here, you're supposed to imagine that you're lying on your back looking up at the sky, I guess, with your telescope, telescopes for eyes, And you see everything expanding away from each other and expanding away from you, but it gets slower and slower, but it keeps on expanding forever. So that was option 1, which would have been interesting if it occurred. And option 2 was a little bit more dramatic, and that was one where the universe slows to a halt and then collapses in a big crunch, and that universe actually comes to an end. So that, once more, you lie on the back and you look up at the stars moving away, and it's peaceful and everything's going away. And then you start noticing that things have turned around and they're starting to come in towards you. And at this point, you start getting nervous. And then, in fact, this universe really does come to an end. So that was a very exciting moment when we thought we would get to put our points on this plot and find out which world we lived in. I thought, what could be better than a measurement where you could find out the fate of the universe and whether the universe was coming to an end. In fact, we were going to find out whether the universe was coming to an end just before the millennium. It was really fun. And it turned out we put the points in the plot, and the answer turned out to be none of the above. The universe is just taking off. So, if you looked at that plot, at that picture, it's expanding, and then it just goes, whoosh, and everything disappears. And, you have to, I've been telling the funding agencies, you have to do all your astronomy now before, while we still get to see the universe. So, this is what led us to where we are, where we seem to be faced with some new component of the universe that we hadn't recognized before. Apparently, the universe is dominated by perhaps a dark energy, which would be some energy spread through all of space that we've never identified previously. We still don't know what it would be, and that it could be perhaps powering the expansion of the universe to be speeding up. That's one possibility. Another possibility is maybe even more bizarre. It's possible that Einstein's theory of general relativity it needs modification, that it's not a finished product, that we're going to have to modify what Einstein tells us about gravity, because that could also explain it. And this has meant that you've not only triggered a huge amount of interest in the popular press, but paper after paper after paper has been appearing on the archives from theorists trying to explain the physics of what's going on. We were counting it is averaging roughly 2 or 3 papers every week for the past 10 years with alternative theories of what could be causing this, and they come with great names for these theories. I love big rift cosmologies and ekpyrotic universe you can barely pronounce. But the interesting thing is that if you ask these theorists, almost none of them, as far as I know, would say that they know what the answer is. They would say, no, they're just opening up possibilities, and they're turning back to us, the experimentalists, and asking, can you come up with some explanation of what's going on? So that brings us to where we are today. And unfortunately, this quote isn't really true. Here at Berkeley Lab, we've actually all been working very hard to do something about this for you. And there are a number of things we can do. The guy will tell you a little later more about the work we've been doing trying to improve that supernova measurement. And that actually we can do a lot more to try and make a much, much more precise measurement. You need to instead of telling apart the universe as accelerating from decelerating, now you need to tell apart universes that have very slight differences of the history of the acceleration and its change from what used to be deceleration to current acceleration, if you're going to understand whether it is a dark energy or a change in gravity. But the good news is that we've also, as scientists, developed new approaches to this measurement beyond supernova. So I'm going to now turn turn over to my colleagues who will David will talk about the next one in line that we developed, which was the gravitational weak lensing approach. And I think it's the combination of these that makes us feel excited that we have a possibility of getting at this bizarre mystery.
Okay. All right, so I guess I should start here with, before the program, we were actually talking about H1N1 quite a bit. And let's assume that statistically, actually, everyone in this room, we're going to make it through it. Good.
Is your mic on?
I think my mic's on.
Yeah, okay.
Okay.
You got it.
Okay. Okay, so I was just saying, statistically, we should all make it through H1N1. So won't worry about that too much. But then if you talk about the very distant future, right, we still don't know what's going to happen. And so for those of you who want to live forever in the audience, and you know who you are, so some bad things will happen. The sun will go red giant in 4.5 billion years, and other bad things will happen. But then eventually, in 100 billion years or 1 trillion years, what's the universe going to look like? And that's what we really don't know at all. Okay, so I'm going to talk about a project that I've been working on for the past 10 years called the Sloan Digital Sky Survey. And this was a project, so this predates our discovery of this acceleration of the universe. This was when we just thought there was dark matter dominating the universe, which is another thing we don't understand that Alexi's going to tell us more about. But this was the first time that we were actually making a digital map of the sky. So up until this time, believe it or not, if you wanted to look at the best data we had for just a map of the universe, the whole sky, the best you could do, well, you could go on campus. There was a copy of these photographic plates taken in the 1950s, 60s, and 70s, and that's what there was. So with the Sloan Digital Sky Survey, this is where we actually applied something modern technology. Let's actually get some good maps of the sky. And the reason to do this at the time actually had nothing to do with dark energy. But what we did was we started by just taking pictures of the sky in a number of different filters. And this has actually been uploaded now onto Google Sky. And so if this animation, we'll see if this animation goes. If this animation goes, this is actually, if you go to Google Earth, you can actually get the Google Sky plugin where instead of looking down, you're suddenly looking up. And this is a lot of data from this project that we did. Okay, so this is just our two-dimensional view of take pictures of the sky. So that's an interesting thing to do. But what we really wanted to do was get a three-dimensional map of the sky. And so I'll get to why we care about a three-dimensional map. But we were doing that with the same telescope. So this is a dedicated telescope for just mapping the universe. And the way that we get a three-dimensional picture of the sky is every galaxy that we're seeing on those pictures, we get a picture of it, we don't know how far away it is. But so then what we have to do is go back and get a spectrum of it. And I'm not going to go into the details of that, except to say the way to do it is to pick off the light to each and every one of those galaxies. Then we send it down through optical fibers onto CCDs and split the light. And so I did bring up, I'll show my one prop that I brought. So we actually bolt these things on the back of the telescope. And gosh, I hope we don't need this one tonight. But you can't see it. There are lots of little holes in the center here. And each little hole is actually drilled very, very precisely to the position of a galaxy that we saw in our images. And then we have a guy, Norm, who actually, he used to clean our toilets, but then we gave him a raise. And now he plugs optical fibers into these holes, and then it goes down to our spectrographs. I kid not. He's done a very good job. I should show a picture of Norm. That wasn't Norm. I have to get a new picture.
That's a wide shot of him. Yeah.
Okay, from that, then we're actually able to construct a three-dimensional view of the universe. And so everyone here has probably seen Star Trek, whatever. You see lots of pretty movies of the universe. There's something different about this one, which is this is your universe. This is all real data. And I have to really remind, even when I give talks to professional physicists or astronomers, they're used to showing simulations of what the universe looks like. But this is it. This is the real sky. So I claim this one is more important than those other ones. And so what we've done is we've created this three-dimensional map with, it's more than 1 million galaxies at this point. And one of the things that your eye can pick out here is you can actually see there are structures. They're not randomly placed on the sky, but the universe actually forms lots of structures. Okay, the next little movie I'm showing here is, this starts up, this would be, this is a simulation of the universe from the Big Bang, where what we want to do with these maps then, don't help me, just play. Help? No. No.
Look off the side.
Help. Okay, help. Okay.
Okay.
Really, I know how to operate a telescope, though. Let's end that show. Oh, okay, here we go.
Previous.
Previous, or is that? Next. Let's go to the next one. Okay. We'll skip that. That was not real data anyway. It didn't matter at all. Okay, so from here on in, I'm just showing more real data. Okay, the reason that we care about making these maps of the sky, well, one of the reasons we care now today is we can, what we found in it is something that we can use as a standard ruler to measure the history of what the universe has done. So Saul was just talking about something that, so he was calling it a standard candle, which is something that we know what it looks like at different distances. We know how bright it should be. We have something else where we know how long it should be. And what this is these are sound waves from the early universe that actually get imprinted everywhere in the universe. So this is, if you go to the very early universe, you can compute from first principles of physics, just, you know, your second grade physics, right, where you have this hot plasma and the speed of sound is the speed of light over square root of 3. You remember all that from second grade. And it travels to a certain point, and this creates these features on the sky. And this is a map of the universe as it was when the universe was exactly 380,000 years old. So I don't have time to explain this, but I'll say this is real. It got the Nobel Prize in 2006, so you know we're not just kidding you. So we see features there. And then on the right, again, this is more real data. This is a slice through that movie that I was showing you of the distribution of galaxies. So each point on there is one of these galaxies, like the Milky Way. And in that, we can see the same features on the left map, so from the very early universe, imprinted on the universe as we see it today. And this is what we're using as our ruler. Now, I should point out, it's a big ruler, so it's a little bit inconveniently long. It's how long it takes light to travel in 500 million years, which means we didn't actually have any maps of the universe large enough to even contain one ruler until very recently. But now we can do that. So now that's what we're doing. Okay, so then looking at the history of the universe, so the Big Bang is in the upper left here. Don't look directly at it. Very bright. But what I want to show here is that so this is the evolution of the expansion of the universe, and we really don't understand a lot of this right now. And so something that Saul didn't mention is there was an epoch in the very early universe where we think it was actually expanding much, much faster than the speed of light. And so this is what we call inflation, not to be confused with other kinds of inflation. But we believe that that happened when the universe was only a small fraction of a second old. Then we went on to the more traditional expansion of the universe for about 6 or 8 billion years. And during that time, what we had was the force of gravity slowing down that expansion of the history of the universe. And then the surprise discovery that Saul made that I didn't believe for a bunch of years, but now I believe him, was that then it started accelerating. And so this is another period of acceleration, and that's what we're calling dark energy. Okay, so I think I'm done there.
Great, thanks, David.
Thank you.
So I just wanted to say how great it is to be here. Can you hear me? Is that good? Can you hear me now? It's really good to be here, and I just wanted to thank everyone for joining us tonight. I'm going to be talking about gravitational lensing. And Saul and David have told us all about dark energy. I'm going to talk about another mysterious component of the universe, which is called dark matter. And the evidence for dark matter goes back to 1933, where Fritz Zwicky, who is this nice-looking gentleman on the left here, studied the motions of galaxies within giant clusters. On the right-hand side, we have a giant cluster of galaxies composed of thousands of galaxies. And the speed at which these galaxies move around is directly proportional to the total mass of this structure. And he looked at the speed of these galaxies and calculated the total mass. And then he compared that to the mass that would be seen through the luminosity, through the light. And he concluded that there was about 160 times more mass than you could see. And he coined the word dark matter and concluded that there was a large amount of matter that was unseen, that was very mysterious. Now, unfortunately, his ideas were not taken very seriously at the time. And part of the reason was probably that he was quite an abrasive character. And he was well known for statements like, astronomers are spherical bastards. And no matter how you look at them, they're just bastards. And he was also famous for saying things like, my colleagues are scatterbrains, sycophants, and thieves. I'm not talking about you. This is Prince Wiki's statement. So this didn't make his theories very popular with astronomers at the time, maybe. So we had to wait until 1970 when Vera Rubin looked at spiral galaxies to see another evidence for dark matter. So what Vera Rubin did is studied the motions of stars as they circle around the spiral galaxy. And what she found is that the stars were moving much too fast compared to the starlight that you can see. And again, she concluded that there was a large amount of matter that could not be seen. So she again brought up the hypothesis of dark matter. So what is dark matter? Well, you think that it's probably a type of particle. Now, at this point, I'd just like to make a distinction here because we've talked about dark energy and dark matter. They're two very different phenomena. Dark energy is responsible for the acceleration of our recent acceleration of our universe, and dark matter is probably a type of particle. We just have similar names for them because we like dark things in astronomy. Dark matter has yet to be detected. We haven't detected an actual dark matter particle. It has two very important characteristics. The first is that it does not interact with light, so it does not emit and it does not absorb light, and it interacts only through gravity. So how do we study dark matter? Well, one of the primary mechanisms we have for studying it is through its gravitational effects. And this is what I'm going to be talking about. This is maybe what your universe looks like on extremely large scales. This is not a real universe like David is showing us, but this is a simulation. It's called the Millennium Simulation. And this is what the dark matter structure of our universe looks like on extremely large scales. So this scale up here is about a gigaparsec in length, and that is about 3 × 10⁻¹² light years. So it's extremely large. And this is a simulation. It's actually relatively easy to make simulations of the universe when we only consider the dark matter, because dark matter only interacts through gravity. So it's very easy to simulate. Now, if this works, I'm going to take you on a little flying tour of our universe. Here we go. So on very large scales, we think the universe is very smooth and homogeneous. But as we zoom in to smaller and smaller structures, you're going to see that it starts to become very clumpy. And it forms giant clumps that we call dark matter halos. They're massive structures of dark matter. And these dark matter halos are connected by these filaments. And we call this whole ensemble the cosmic web, comprised mainly of dark matter. Now, where does the normal matter lie? The stuff that you're used to, this normal matter, lies at the center of these giant clumps of dark matter. So typically, this structure here would be a giant cluster of galaxies like the cluster I showed you in my first slide, and it would contain thousands and thousands of galaxies, and then maybe these small things out here would contain individual galaxies. So basically, the normal matter is resigned to stay within the gravitational scaffolding of the dark matter, because the dark matter makes up most of the mass in the universe. So galaxies form in these little pinpoints of light here. And the reason that we have this filamentary structure is because the universe very, very early on was very homogeneous, but it had some small variations in its density. And eventually, as the universe evolved, these structures began to collapse under their own gravity, forming these dark matter halos that we saw. So what is gravitational lensing? Well, I've showed you in the previous slide that the dark matter is clumpy. It forms these giant clumps of dark matter. The second piece of information is that we know that Einstein's theory of general relativity tells us that mass can warp space-time. So this is an image of some very massive object, and it's warping space-time around it. And as a result of this, the light that travels from a distant galaxy follows the curved lines of space-time, and its trajectory is also curved. And this is gravitational lensing. So as a consequence of this effect, if we have a big giant dark matter clump here and the dark matter clump here, the light from a distant galaxy will not necessarily travel in a straight line. Instead, it will come towards us following some curved path. And this is exactly what we call gravitational lensing. And this tells us about dark matter, but we can also use it to study dark energy. So I also have my little props here that I brought with me today. I have my standard candle. That's all.
Made out of whale blubber?
No, couldn't say that in Berkeley. And I'm also French by nationality, so I always have a wine glass handy just in case. You never know, so I'm carrying my wine glass with me. And I'm going to use this wine glass to demonstrate a very easy optical analogy of a gravitational lens. And you can also try this at home over a candlelight dinner. If the conversation's getting very boring, you can demonstrate how well you know gravitational lensing. Let me get this to go. So basically, the idea behind gravitational lensing is that you're looking at the light traveling towards us from a distant source. So in my analogy, the candle is a distant galaxy, and I'm an astronomer on Earth looking at this distant galaxy through my telescope. And in between us, there's a giant clump of dark matter, which acts as a gravitational lens. In my analogy here, we're looking through an optical lens, which is basically a wine glass can be an optical lens. And as I look towards this distant galaxy here, I'm actually seeing, I don't see the flame, the candle flame as one single entity. Instead, I can begin to see arcs and features like rings. Now, I can't show you this, but you can try this at home. And if I go back to my analogy here, then, lost my pointer.
Wait, underneath the candle.
Oh, thank you. So going back to my analogy, this is the light traveling from a distant galaxy. And we see features like rings and arcs instead because the light has been deviated through the medium, through the lens. And this, on the left-hand side, is actually a real image taken by the Hubble Space Telescope. The central bright yellow clump is a galaxy. This is not a spiral galaxy that you're used to seeing like. It's more like a rugby ball galaxy. And the blue features is a real galaxy that's situated behind the first galaxy. And you're seeing these arcs and spherical features that you can also see in the wine glass. So this is gravitational lensing. So what do I do for a living? I basically study galaxy shapes. And this is just a little illustration to get you to understand gravitational lensing a little more. If we could make a wallpaper of galaxies and place a giant clump of dark matter in the foreground, that's exactly what we would see. We would see, if we could move this wallpaper, we would see that the shapes of the galaxies are distorted in this spherical pattern. We see a ring and we see arcs, and all these shapes are distorted. And by studying this effect and the amount of distortion here, we can say something very precisely about the amount of mass that is located in the foreground. This is a giant galaxy cluster called the Abell 2218 galaxy cluster, and it's composed of thousands of galaxies. And the mass contained within this cluster is so extremely massive that it creates a gravitational lensing effect here, and you see these arcs of light that are distant galaxies which have their shapes highly distorted. By studying the position and the amount of stretching of these distant galaxies, we can measure very precisely the amount of mass here. And surprise, there's much more mass than you can actually see in the light. So most of this cluster is actually made out of dark matter, and the light that you see is only a very small component. This is another optical analogy. This is one of the most famous results from gravitational lensing concerning the evidence for dark matter. This is called the bullet cluster. And in order to understand this result, you need to know two facts. The first fact that you need to know is that a cluster of galaxies contains two visible components. It contains galaxies, these are the little yellow golden blobs, and it contains hot gas. And this hot gas emits X-rays, so we can detect it. The second fact that you need to know is that the hot gas is actually a lot more massive than the galaxies are. So that's where most of the mass lies. Now, this system is very intriguing because it's actually two clusters of galaxies that have collided through each other. It's a giant cosmic collision. And when we look at the different components, these are the galaxies. We basically see that the galaxies have passed through each other during the collision. And the reason for this is that there's actually so much space between the galaxies that they almost never bump into each other. They just go right through. However, when we study this system through gravitational lensing, we can demonstrate that most of the mass is located at these blue peaks here. That's where the mass is located. However, when we look at this in X-rays, so we're looking at the hot gas component, what we see is that the gas has slowed down as the two clusters collided because the gas interacts electromagnetically, and it's slowed down, and it's even formed a beautiful shock front here. So what is this telling us? Well, this is telling us something very exciting, and you have to remember the second fact that I told you, which is that most of the visible mass is located, is the hot gas. What the lensing is telling us is that that's not true. Most of the mass is located around the galaxies here. That's where most of the mass is. And we learned two things from this. One, there's a lot of mass that is unseen. We don't see it. And secondly, it doesn't interact with normal matter. Had it interacted with normal matter, it would have stopped and been slowed down here. So those are two pieces of very important information regarding dark matter. This is another exciting result from gravitational lensing that comes to us from the Cosmos survey, which is a very large survey done with the Hubble Space Telescope. And the size of this image is about 9 times the area of the full moon. What we have done with this survey is study the shapes of more than 1 million galaxies and studied their average shapes and distortion patterns to reconstruct the entire dark matter along the line of sight. And this dark matter distribution is shown by these white contours here. And what we're seeing is that the observations are telling us that it looks very similar to what we think it should look like. We have giant clumps interconnected by these large filaments. This is basically, we're trying to look at the cosmic web that I showed you earlier in that giant pink sponge-like simulation. And there's another second thing that's interesting here is that we can compare the location of the stars and the galaxies and this hot gas that emits in X-rays. And we find that all the normal matter, this is all normal matter, is located within the dark matter scaffolding. So this is, again, a nice demonstration that we know something about the universe, or we think we do. The normal matter is confined to lie within the gravitational potential wells that are defined by the dark matter. So where do we go from here? Well, there's a couple of experiments that maybe we could talk about afterwards that Berkeley Lab is involved in that have to do with measuring weak lensing more precisely, with measuring baryonic acoustic oscillations more precisely, and also supernova, so that we can learn more about both dark matter and dark energy.
Wow, thank you very much. I'm going to ask folks, if you have questions, go ahead and start lining up. I got a couple of questions first because this could go right over my head. But there are microphones at both sides and up above as well. The first question I have, Alexei, is you said that the dark matter doesn't interact with normal matter. Does it interact with itself? In other words, does the dark matter bump into itself as well?
It could do. Now, just like dark energy, we have many, many theories for dark matter. And there's no leading theory right now. There are lots and lots of there's a whole zoo of different particles that are dark matter candidates. Some of these particles could interact with each other. In some cases, they could be their own, it could be its own antimatter particle, in which case, if it did hit each other, it would actually annihilate and turn into gamma rays or something that we could observe. But that's just one candidate among many other candidates.
Now, have you seen that? For instance, in the bullet cluster. Here you have these two large volumes of gas and stars merging into one another. Do you see the evidence of dark matter maybe annihilating itself?
Yeah, that's something that's extremely far away, so we can't study that, something that's that far away, but we are looking for this annihilation signal at the center of our own galaxy, because the center of our own galaxy would be where the dark matter would be most dense, and so that's where the probability that two dark matter particles would collide would be the highest, and so we have telescopes pointed in that direction looking for such a signal.
Cool. Is there a question? Yes, sir. Please.
So this is directed mostly at Saul, but anyone can feel free to answer. So for me, just intuitively or whatever, the idea that the universe may be sort of expanding, and then that expansion might slow and then contract into the big crunch, or I think a gnab gib is what Douglas Adams called it. That idea is kind of cool because, maybe the universe could be like a spring and just sort of expand and contract, and that gets rid of all sorts of philosophical questions. So for me personally, I think that would be cool to see. I know scientifically that's not what the data shows us, but for any of you, not as scientists but as people, do you have sort of fates or stories that you would like to hear about or learn about through the data? I know that it's not a scientific question, but just anything that sort of inspires you.
I can take a cut at it. I was going to say that I think that these oscillating, or cyclic universes are not ruled out either right now. It's because there are ways in which you can get a universe that would look like the current universe that came from a previous contraction and then expansion. There's a very nice, fun one that's being worked on of that kind at the moment. For me, the funny thing is that I remember at one point, people would ask, well, which would you rather, a universe that would collapse, which did you like to feel, or the one that would expand forever? And I found myself thinking, well, I don't know, they both sound kind of bleak. One's sort of empty and cold and bleak, and the other is either hot and fiery and scary, and so on. So I'm not sure any of the long-term prospects sound great by themselves. On the other hand, I would say that there's some of the theories that are much more fun to think about, and it would be great if it turned out the universe worked that way. But as an experimentalist, we have to, I have to keep saying, well, I'm not going to play favorites. I'm going to let it go. Personally, I think it would be wonderful if it turned out that it was one of the extra dimension theories. I think that would be a really fun one if it turned out that really, what's going on is that gravity is leaking out into some other dimension, and we're not ordinarily aware of, except we've now discovered it because of the acceleration. But I also enjoy some of these oscillating ones too, for some of the reasons you're describing, because you can imagine something which has sort of an eternal existence and sort of gets rid of worrying about beginnings.
You're looking at things that are very, very, very far away, and the signals are pretty faint. How sure are you seeing what you think you're seeing?
Yeah, so
I have a question for you. This is for Dr. Saul and Alexis.
We might follow this one first. Do you want to go, or should I?
Yeah, well, I'll just say that when Saul's results came out as far as the accelerating the universe, most of us didn't believe it at all. And one of the reasons we didn't believe it was the signal that he saw was that all these very distant objects were a little bit fainter than what they should have been. And so if something's a little bit fainter, it's easier to invent, oh, maybe there's just something going on out there. Maybe there's just a little bit of gas or dust between us and these distant galaxies. So that was a lot of initial skepticism. But now we've actually come at the problem from different angles, and we know how careful Saul was in the first place, so now we actually believe it.
Thanks. Was there a second question?
I have a comment
Yes.
for Dr. Saul and Alexis. I think what you're alluding to is a mere reflection of matter in the exploded realm, and so that what you perceive as dark matter being an acceleration is actually the photonic reflection of matter exploding unto itself. And so you have a situation here where we haven't yet detected the particular or dark energy. So My question would be, will we need a chilled argon detector or a gravimeter in orbit to detect this type of energy?
Can I say something about this? So I just wanted to clarify one thing, in that the dark matter and the dark energy, as far as we know and the way we're thinking about it right now, are probably two very separate things. And actually, the dark matter does not cause the acceleration of the universe. In fact, it would be the opposite. The dark matter, it has a mass. Therefore, it has gravity. And had we no dark energy, it would contribute to making the universe contract, maybe back to a big crunch model. Dark energy is the opposite. It's a form of negative pressure. It makes the universe accelerate in its expansion. So they actually have competing effects.
Could you call it singular energy?
Saul?
I said, you're asking, could you call it singular energy?
Singular, yes. From black hole singularity.
Is dark matter black holes? Would that be the question?
That's one version, yeah.
There are some ideas that dark matter could be formed from very small black holes that were created very early on in the universe. They'd be called primordial black holes. But since then, Stephen Hawking came up with a brilliant idea of how to kill black holes, and basically they can lose energy and they can eventually disappear through a process called Hawking radiation. So it's unclear whether any of these tiny black holes would actually exist today anymore, and we haven't seen any. So I would say it's not a leading theory right now.
There, yes.
Yeah, can we have this? So my question, I watch a lot of science shows, really, but I noticed on one of the shows that I watched that there's kind of like a speed limit. The speed of light is in the universe. And I noticed that one of the slides in the beginning, you mentioned that one of the ways that you guys might have to, resolve this issue is to kind of modify Einstein's theories. And I mean, from what I see, or from what I hear, he's kind of like, his general theory of revolution, or you know what I'm saying? It's kind of like the Bible as far as you guys are concerned. So more than anything, I'm just kind of curious if you guys see that more as a hindrance when you're trying to think of stuff as outside of the box. I know you guys can't go away from that really. How does that really work with what you're doing?
Well, we should point out that I guess maybe this kind of situation is one where you want to preserve all the good parts of Einstein's theory of relativity. I mean, it's been amazingly successful at explaining all sorts of things that we could never otherwise explain. So anything we do to modify gravity has to keep most of the theory intact, because we know most of it really works very, very well. The modifications that people are trying out are ones where they wouldn't affect things, for example, on small scales, but just on very, very large scales. And so that's one thing that you could potentially look for in the kind of work that Alexei's doing.
Yeah, gravitational lensing could be sensitive to the effects of modifying gravity on very large scales, and I think that's something that's really exciting. It's something that we've only barely started to study now, and something that's extremely difficult to study, but this technique does have the potential of looking at that kind of question.
Most of the theories that I've seen people trying out don't yet work. They're not completely consistent, self-consistent, and so I don't think the theorists yet feel like they have a good alternative to Einstein's theory. But I will say the ones they've been trying out tend not to change the speed of light as a speed limit still. So that tends to still exist in these theories that they're working on so far.
Well, one of the things that Einstein talked about, or at least people who worked on his theory have discussed, is gravity waves. What's up with them? How come we haven't found a gravity wave yet?
Well, gravity waves are extremely difficult to detect. We're building detectors to look at this effect, and there's actually some people in the audience up here that study gravity waves up on the second balcony there. And I'm just going to repeat to you what he's told me, but we have these instruments called LIGO and advanced LIGO that are trying to detect a gravity wave, and the precision that you need is extremely high. So you'd be shooting light out for kilometers and having it come back to you, and you'd try to detect kind of a movement in space that would be of the order of an atom.
Or the nucleus of an atom.
The nucleus of an atom. So it's difficult. Difficult job. We're working on it.
So, yeah, I think if we had detected that by now, well, that would be pretty amazing.
Yes, it would be amazing. There are other ways to study it, looking at pulsars, but it's extremely hard, so we don't have any results there yet.
Another question down here. Yes, sir.
Hi. Thanks for this great presentation. I was reading in New Scientist actually just today, and there's a very interesting article that I would like to ask a question about. And this kind of, maybe this is for Alexei, this goes to, you were talking about this Cosmos survey that
yes.
I believe Hubble was doing. And there's a researcher whose
Rachel
name is
Bean.
Rachel Bean, yeah. And the idea here, and this goes back to the gentleman above who was asking about Einstein's theory of relativity, and apparently maybe it says here that some time in the past, relativity is supposed to, I think, no, mass is supposed to warp both space and time equally. Now, I don't really understand that per se, but that this lady found that between 8 and 11 billion years ago, gravity's distortion of time appeared to be 3 times as strong as its ability to curve space. Can you
You're in
comment on
luck.
that?
This lady knows a lot about that.
I'm really glad you asked that question. I knew someone was going to ask this question. This result is based on the data set that I'm working with for the last maybe 7 to 8 years now. The Cosmos survey, which is that large survey with the Hubble Space Telescope. And one thing that we've looked at is we study the weak lensing signal, the lensing signal, and we look at it as a function of distance or as a function of time. And we've studied how that signal varies from now until half the age of the universe. And what Rachel Bean is the person who published this paper recently, has looked at this data and found that you could explain some of the discrepancy by introducing a form of modified gravity on very large scales. And having worked with the data, I need to issue a note of caution here. And the reason for this is that the paper that she published is based on results we published about in 2007, so a couple of years back already. And since then, we've been working on new versions of our data set, and especially the key thing that we've been looking into. So David has told us about how we can image galaxies on the sky, but we don't know how far away they are. And we've been working into figuring out to higher precision how far away they are. And this actually makes a difference for the type of study that she's published. So we're hoping to publish a new result within the next couple of months to see whether or not this signal persists. And I think it's a very exciting field. I think this is a really exciting question to be addressing. But you have to realize that these are extremely difficult techniques, and we're just starting to scrape the surface here and to try and measure these kind of things. So come back in a few months and ask us about it.
Oh, good. We'll have breaking news. Yes, sir, please.
I have a question for Alexei. If we assume that these clumps of dark matter are randomly distributed around the universe and that they distort starlight in a sort of a zigzag pattern, a random pattern, not even a pattern, a random path, how can we tell where anything really is out there, A? And more importantly, how can we tell the distance? Because we're not looking at straight line path of light.
Yeah, so that animation I showed you had lots of squiggles. Most of the time, the light will only encounter maybe one giant blob. And if we look around this one giant blob, first of all, there are very distinctive effects that we can recognize those arcs. Those are very distinctive, and we can use those to study the mass. Now, what also happens is that if you take a giant blob of dark matter, you can also study it a lot further out from the center. And you'll have these very small distortions of the shapes of galaxies into a circular pattern. And most of the light that travels from that distant galaxy will actually only be deviated by that one massive structure.
But we don't know the mass of the structure, do we?
We can deduct it from this technique that I'm telling you about, the gravitational lensing. The amount of curvature that's introduced is directly proportional to the mass that's along the line of sight.
Does that presuppose that you know where the star actually is?
Oh, yeah. So we can also learn about where these galaxies are using the techniques that David's talked about. So you get a spectrum of the galaxy, and you look at features in the spectrum, and this tells you that that galaxy is actually behind the massive structure and how far away it is.
So I should add, so most of the deviations, they're they're really quite small. So it's really, if you're talking about lenses, if you just took your window pane at home and looked through the glass outside, there are small deflections just from imperfections in the glass, and that's
Here's the window pane.
Yeah. So anyway, so that's most of the universe.
So this is true. We can look at giant structures and study very strong deviations, but we can also look at the universe, just the average statistical signal that we see, and this tells us about both dark matter and dark energy. And the analogy here is looking at through some image through a distorted window pane and trying to reconstruct what the properties of the window pane are if you knew what these houses look like. Great window pane analogy.
Yes, sir.
I
beg your pardon. May we go upstairs? We'll get to you next.
If the universe is expanding on a cosmological scale, does that also mean that it's expanding on a microscopic scale? Are the distances between the atoms and molecules getting bigger, and are the atoms and molecules themselves expanding?
Generally, no. I mean, it would be the case, except for the fact that the energies of gravity that are pulling things together are much, much more important than this expansion repulsive energy due to a hypothetical dark energy. So the current understanding is that almost anything that's bound in some system, electrons to their protons in an atom, stars to their galaxies, those things, the binding energy is much, much more important than the amount of energy you get from the dark energy that's in that system. So at those scales, there is no real impact that we know of at this point.
Are we sure? Because our rulers will be getting bigger too, right?
Well, obviously, many of these things you have to do based on your simplest hypotheses. And so you begin with, what do you think is the simplest picture of the universe that we live in, and then you try and modify it slightly, and to see whether you can explain what you get. Now, someday you may get forced to a position where you realize that's actually a rather dramatic explanation that you're going to need to explain something. So far, we don't think that's the case in these respects, and that we have very precise measurements of behaviors of things on small scales and solar system scales, which suggest that those parts of the story are fairly well covered by current theory.
Thank you. Yes, sir.
My understanding of, layman's understanding of quantum physics is that one of the most significant discoveries in the 20th century was that when we looked deep into subatomic particles, that they weren't actually discrete entities, but were more accurately described as like condensations of a field. So I'm just curious about when we are looking at dark matter, why are we assuming that it's a kind of particle and not a field? Or is there a place for a field concept in dark matter?
If no one else will answer. I mean, so all we do know is that it's interacting via the force of gravity with everything else. And the approach that you take when you know very little is you're starting by assuming the simplest things. And I mean, by particle, we really just mean it is something interacting via gravity. Though, I mean, it would actually be, I don't know if it would be everyone's hope sitting up here, but it'd be my hope that what we've just started picking away at is something that might actually contain a lot of very rich physics. So, we kind of talk about the dark matter particle as if, there's a particle and it could go by all sorts of different names. And the way we talk about it is just the most simplistic thing that's permeating space. But it might not be that at all. It might be, we were talking earlier about, do these particles or whatever they are, do they interact with each other? And maybe they do. And maybe they do in very complex ways, just like we do. And maybe there are lots of other forces associated with the dark matter particles also. And, boy, that'd be fun if you had the dark matter universe sharing this space-time with us right here, and our counterparts were, in the other dimension talking to each other. I mean, we don't know.
We don't know a whole lot.
I'm guessing here that you're sort of scratching at the edges of the theory of everything.
I mean, one of the real excitements in our field at this point is the fact that this may be one of the first clues we have that will help us get the next step forward in our understanding of physics. Because right now, we've reached the point where physics has gotten so good at predicting many decimal places of what we see around that the standard model of physics is hard to break. And it's also hard to figure out how to get that next step beyond. Right now, we haven't been able to figure out how to combine, for example, the theories of gravity with the theories of the other three forces. And that's been a very tough one. Einstein worked at it for many, many years to try and get a theory of everything. We're hoping that some of these mysteries, like dark matter and dark energy, might just be a hint of a place that if we can crack that, we might get some solution to these bigger physics questions, such as you're asking.
Yes, sir.
This question, actually, I wanted to ask before I walked up, but it segues perfectly on that statement. So you build fantastically complicated, beautiful instruments to look at things far, far away to uncover these mysteries. Do you expect, and even if you don't expect, do you hope that experiments on the Large Hadron Collider, for example, will throw light on some of the questions you're asking?
Well, I think particularly dark matter, do you want to take the words? Yeah.
It's a possibility that we will find maybe one of these dark matter particles, if they are a particle. I think, to answer both of your questions, one of the reasons that we are exploring this idea that it's a dark matter particle is because it's one of the best explanations that we have so far. And there's a lot of people who are working on building extensions to the current standard model of particle physics. And in these extensions, you find natural candidates that have the properties of the dark matter particle. They're massive, they don't move too fast, and they don't interact very strongly. So we have candidates out there that we think we could work. And whether or not if the LHC, Large Hadron Collider, ever turns on again, it'll be very exciting if they discover it, but we don't really know because there's a large number of candidate particles out there. If they do discover it, it'll be very exciting.
Yes, sir.
Yes, thank you. Good evening. My question is a general question. It has to do with the expansion of the universe, which is sort of now, I think it's commonly believed that that's what happened. But is there a mechanism that can lead to the explanation of how matter is moved multiple times the speed of light during this expansion? Is there a mechanism? And what is that mechanism? And could you expand on that, please?
So to speak.
So you're talking about seeing galaxies recede and...
No. I'm talking about the expansion phase of the universe.
Inflation.
The expansion.
Hyperinflation.
I mean, one thing that's important to mention is that in an expanding universe, in that model I was showing before, if you think about it, any location in space is standing still. I mean, from its own perspective. It's just that the distances between any location are increasing. So it's not that things are moving faster than the speed of light. It's just that space is appearing between me and Alexei and except not in our case. Things that are not bound together. You're pumping space in, and any 2 points then, from their own perspective, are standing still. You don't violate any speeds of light. It's just that you start building up as you go a little bit further and a little bit further and a little bit further. You start building up more and more and more space, that you can pump extra distance in. That gives you an illusion of things moving faster than the speed of light, and they certainly get further apart quicker than the speed of light, but they're not actually moving through space, which is what Einstein's theory forbids.
So the idea is that this inflation really is just extra stuff, extra space being put in between things.
But so there is, in addition to this, so that's the universe expanding today. So it's, the piece that doesn't really fit is if you look at a part of the universe very far away in that direction, a part very far away in that direction. They've never seen each other, right? We're just seeing them because it took that light, the age of the universe, to reach us. Yet, they're the same temperature. They look basically the same. And that, there's no, in the kind of the physics world, there's no natural explanation for that. And that's what's led to this hypothesis of what we call inflation, which would have been something that happened in the very early universe where the whole universe was homogenized before this inflationary epoch, where again it's not things moving faster than the speed of light, but it's it's space itself expanding very rapidly. At least that's the current explanation, but I admit it's not.
It's hurting my head already. Yes, ma'am.
If dark energy and dark matter are two competing opposites, how do they exist in the same universe?
Oh, well, of course, there are lots of things in the world that compete with each other in our universe today, and so you can certainly have things that work against each other in a universe. In this particular case, ordinary stuff gravitationally attracts, and it would tend to slow in expansion. Whereas if space itself had a internal repulsive energy that makes it want to reproduce faster and faster, and make more of itself, that would then fight against that tendency for the stuff to attract each other. So one's, you could think of as the stuff tending to pull together and the space tending to push apart in this particular case.
And my other question is, if the universe is expanding, where does the extra space come from?
Right, well, and remember the picture I was showing you, you're pumping extra space between all the points. So it's not that you're adding any space out there, it's that internally we're putting more space in. And it's the inventor of the inflationary model that David refers to, well, one of the inventors, Alan Guth, refers to as the ultimate free lunch. That you apparently are able to convert what is a one form of energy in space, which is the curvature of space, to extra extra space between things. In some magical way that we don't we certainly don't have much of an intuition for. I don't know anybody who has an easy way of imagining it in their brains.
But if we could do it in our Berkeley houses, that'd be great.
Yeah. Yeah, I knew it was magic. Yes, sir.
Go ahead.
Thank you. I want to take a point that Saul was making and turn it around to Alexei, if I understand it correctly. That one possible explanation for dark energy was that gravity was leaking out to another universe. And I'm wondering if possibly dark matter could be matter in another universe giving its gravity to us.
Yes, that's entirely correct, and that's a great question. And there are theories that try and explain dark matter through other dimensions, and that's a that is a possibility.
There's nothing observationally that rules it out at this point. Okay.
Wide open.
Very good. Thank you.
In fact, many of you pointed out that many of the theories, the biggest problem is that there's so many of them. I was mentioning to you that there's 3 a week for the last 10 years on dark energy alone, and that doesn't count the ones that are on dark matter in a time period. So we don't have any paucity of fun theories. What we need is extra data to help us carve a direction to pursue amidst all these myriad theories.
Exactly. One of the difficult things about what we're studying is that really most of the manifestations that we see are cosmological. They're in galaxy clusters or very large volumes of space, and it's difficult to make these measurements. So we're working really hard to make measurements that will try and nail down the parameter space of the theories so that theorists can come and say, oh, this is what I have to work with. But now the parameter space it's really big. For both dark matter and dark energy.
But we should say we know a lot more than we knew even a few years ago on this. So
very true. Yes.
As far as dark matter goes, so Alexei had some real maps in there somewhere. Somewhere there's real data. So this is really our first mapping of where the dark matter actually lives. And so this is something we weren't able to do up until just a few years ago. So our hope is that this, picking away at this problem will actually teach us something.
And we have ruled out a lot of theories already of dark matter, and for that matter, some of dark energy.
For example, for dark matter, we used to have an idea that dark matter was a hot particle, that it moved extremely fast. But through observations, we've nailed that down, and we now think that actually it's not a hot particle, it's probably cold. It doesn't move very fast. So that's part of our narrowing down this parameter space.
Yes, sir.
So we know that matter causes space to curve, and the gravitational lensing seems to assume that if space is curved, then there must be matter there. Is it possible that there is something else that causes space to curve, and this is why this dark matter that we're attributing this to doesn't interact with other matter?
So I would say that that would be going back to this question of modifying Einstein's theory of general relativity, because so far most of what we do assumes that this theory is correct. And the reason we assume that is because when we measure it in the solar system, we can measure it to extremely high precision and it's still valid. So we think it's an extremely good theory. We've measured it to, you know, with probably like 18 zeros and then a 1 type of precision. It's extremely precise. Now, I think what your idea is pointing towards to is maybe there's a different theory of gravity that would change the warping of space-time in some way, and maybe that's true on large scales where we have difficulty making these type of measurements. We can't send light rays between galaxies back and forth without waiting a very long time for them to come back again. So, and that's something that people are working on. That's a current problem. Now, I think most people would say, maybe Saul and David can back me up here or not, that that's a really good way to try and explain the dark energy. It's maybe not a great way to explain the dark matter, given what we know today. Do you agree?
No, I think that at least the way we're thinking about it now, that's probably the way to bet. You know, if you're going to guess.
Well, we know the dark. We know the dark matter. It's clumping because you've mapped it.
Yes.
You can see that it's clumping.
It's clumpy.
There it is. There's the proof. Yes, sir.
Thank you.
Going back to the theme of parallel universes, is it possible that some of this or much of this dark energy is coming from a mutual annihilation of normal matter in our universe with an antimatter universe, say through like Higgs bosons, which I understand are theorized being able to move through different dimensions? Maybe they're just hopping across from our space-time into this nearby universe of antimatter.
I think it's a little hard to make an annihilation kind of theory work because then you would actually presumably see the photons from the annihilation rather than seeing a repulsion. And photons don't have a repulsive effect on the expansion of the universe. And so ordinary material, even annihilating, doesn't have that effect on the expansion of the universe. So those are probably not the uses that we would use of other universes in these theories.
Do we have a question up here?
A question, yeah.
Yes?
Try.
Oh, okay. I was wondering if antimatter ties in with any of the theories with dark matter, or if antimatter could possibly be connected with dark matter.
So probably not. And the reason for this is that what our observations are telling us is that the dark matter doesn't interact with normal matter. If you throw normal matter and dark matter at each other, they just kind of pass through each other without seeing each other. Now, if dark matter were antimatter and you threw it at normal matter, you'd have a really big explosion. So we would see that happen because when they come together, they annihilate into large amounts of energy. So I think that would probably be the best explanation. We don't think it's antimatter.
We have more questions. I want to get. Oh, I'm sorry. Upstairs, please.
So on the scale of very large and scale of very small, I'm pretty convinced by now that you guys have a lot of mysteries on your hands. I'm wondering if the three of you could just sort of toss out, are there any experiments or projects underway, whether or not you're involved with them, that you're just on the edge of your seats waiting to get the results back because it's going to fill in some variable?
Boss. David?
Well, so I should say that the only thing that could make that we'd expect a dramatic potential find in the very near future is the Large Hadron Collider, right? And that.
What? The Large Hadron Collider. I think your mic is falling down.
Oh, sorry.
So there's a large experiment in Geneva that's banging particles into each other called the Large Hadron Collider, or the LHC.
Right. So when this turns on, sorry about that. So when that turns on, hopefully in the coming months, that has the potential for finding, for example, a dark matter particle. aside from that, the other experiments that we're talking about as far as measuring properties of dark matter and dark energy, it really is, these are, I think, longer-term projects, we think at the moment, where we're really trying to design the next generation of experiments right now that will be picking away at these problems a little bit further. What I should say is, as far as dark energy, our mapping of that right now, it's really in the kind of in the cosmology point of view, it's in the local universe where we're seeing it. So we've taken observations like, well, the 3 different methods that we were talking about, and we've mapped it out some number of billions of light years, which sounds big, but when you go back to the furthest that we can see is the cosmic microwave background, that's 13.7 billion light years away. And most of the intervening age of the universe, we haven't actually mapped out. And so, so we're really eager to do that.
Yes, sir.
Hi there. It's a 2-part question. Number 1, they say as above, so below. And do you think there's a black hole at the nucleus of every atom, as well as the nucleus of every galaxy, and that binds the atom and provides a gravitational force that holds the proton-neutron center and the electrons around their orbital shell? And the second question is, do you think there's a black hole at the center of the sun and our planets? Because the sun is constantly exploding. You think it would just destroy everything, but yet it's at the same time holding the planets in their orbital shell around the sun and holding the sun together. And as atoms go over the event horizon into the black hole, the stripping of electrons off the proton-neutron center releases energy, releases radiation that is known as sunlight. So do you think a black hole's at the... what about my black hole questions?
I can answer the first part, and then maybe someone else can take the second part. But so is there a black hole at the center of the nucleus of an atom? Well, first of all, we have to think about how that black hole would get there. It's actually difficult to create black holes. Now, we do know that you could create very tiny black holes at the beginning of the universe, but we've also learned, thanks to debates with Stephen Hawking, that they disappear quite quickly. They actually die. So a black hole, a very tiny, tiny black hole would actually evaporate and would disappear. And then about the black holes at the center of the sun, well, the way we think black holes are actually created is by suns, massive suns, maybe 3 or 4 times the mass of our sun, exploding and then leading to a black hole. But we don't think there is a black hole before it explodes. Maybe you want to elaborate?
Yeah, well, I should say, so the sun is actually a very well understood entity. So as far as the physics of just what the particles are doing in the center of the sun, so the temperatures, the densities, everything like that is very well computable and matches what we see both just from light coming out of the surface of the sun, the amount of light coming out of the surface of the sun, and then there are other kinds of observations that fit very, very well. So a black hole being in the sun, I think, would be inconsistent with all the data that we have.
Probably not's the answer. Yes, sir.
Yes, I've noticed that astronomers speak quite freely of the idea of expanding space, but I still have a lot of trouble with that concept. As Saul said near the beginning of all this, that is really mind-boggling to think that space itself can expand. I've always sort of naively assumed that space is nothing, and I guess I learned in 2nd grade that twice nothing is nothing. So I don't understand how nothing can become bigger unless it's actually a something, which leads me to think that space is actually some sort of fabric that is stretchable or something. So I don't know. Can you address that? Thank you.
I mean, to some extent, you're touching on, I think, some of the fundamental mysteries of the sorts of things we're working with. These are very difficult concepts, even to figure out how to analyze, because you start asking, well, what do we mean by space? Is it just the distance between objects, or are we actually talking about the stuff of the space itself? We do know that in a modern quantum mechanics picture of empty space, it's not a very empty place. It's full of virtual particles appearing and disappearing before you get a chance to look at them. And that hum of particles appearing and disappearing itself acts as what Einstein called the cosmological constant that I was mentioning earlier, and it also could act as the thing that would expand space and make it reproduce even faster, which is the bizarre consequence of having that hum of empty space. So you're picking at, I think, or you're pointing out the place where a lot of these mysteries and a lot of these theoretical questions lie. We currently think that it's actually very difficult to have that hum of empty space be the only explanation for why the universe is accelerating. Just to take a little further the thought. And that's because if you do a naive calculation of how much that hum should contribute to the expansion, it's way too much. You get numbers like these ridiculous 10 to the 120 times off from what you would have, what we actually see. You would have expected it to be much, much more acceleration because of that. And therefore, there's always been an assumption among particle physicists that there will turn out to be a perfect cancellation of that particular effect. But apparently, it's not so perfect. And so we're trying to figure out why.
Up above? Yes.
Hi. Right. So this is a bit of a simple, not very scientific question, but okay, two things, I guess. How can we learn more, and how can we be involved in anything, like if we, think of things, ideas,
I think the question is how can we learn more, and how can we be involved?
How can we follow up on all that we're hearing tonight?
So
I know you do more of these.
There's some great resources on the web. The Berkeley Lab website has a lot of information about some of these things. I would do Google searches if you're interested. There's really a lot of resources out there.
Question over here.
Sorry.
So I would say if you can stomach it too, Hawking's writing is actually very good. So I know his books are some of the most. It has the smallest ratio of being read to being bought, but it's actually very much where I think it's just people don't get over the cracking the first page, but once you do, it's actually very readable.
And I was going to throw the idea out there as well. If you want to help out, we don't have any projects with dark matter and dark energy right now, but there are people who are studying galaxies, and you can go to a website called Galaxy Zoo, and you can learn how to recognize different types of galaxies and classify them. And this has actually been some really exciting work done by you guys, and with lots of very interesting papers published on this. This is something that you can, if you're interested, you can go home and classify galaxies all night.
And in fact, just recently, one of our colleagues who's working with us on finding the supernova has put our supernova searching into this website as well. So the Galaxy Zoo website can point you to a place where you can actually look at galaxies and see when they find a supernova as it explodes and help classify which ones are the supernova and which ones are just junk.
So we do have the problem here that the universe happens to be very, very big. And so when we make these maps, it's more data than any of us could possibly ever look at. So that is one of our conundrums.
Let's go to the balcony one more.
Before it expanded as much as it did, everything was closer together, so gravity was much more important. Everything felt much stronger gravity. And so in the first half of the lifetime of the universe was slowing down due to Alexi's dark matter. So it had been slowing down for about 7 billion years, and then it got so dilute that the gravity wasn't that important anymore, and then the dark energy, we believe, would have taken over, and it's been accelerating for the last half of the time. So it does change, or it has changed in the past, and we don't really know whether the properties of dark energy are staying constant or not. That's one of the things, in fact, the projects that we're working on should be able to map out to see how constant that the properties of dark energy are, and whether it's had the same acceleration over that 7 billion years, and whether it will or not. So that's something we can actually find out.
And then the second part of my question is it thought if it will continue to accelerate or increase expansion, would the speed of light be a speed limit, as the gentleman earlier referred to?
It'll be the same issue that we mentioned before, that no particle itself will ever get faster than the speed of light in these theories, but points across space will appear to move apart from each other faster than the speed of light because you're pumping space in between them. So that will be possible.
Yes, sir.
Hi, commenting from the perspective of the elegant universe or hyperspace, and the idea of string theory being that dark matter could be like a three-dimensional reflection or a shadow of higher dimensional objects or creatures, or can you give any comments on that perspective? Do you know what I'm referring to?
Your dark matter.
My dark matter. I can't tell you a whole lot. It's not not a string theorist, but you're absolutely right. There is the one idea is that dark matter could be a form of an extra dimension that we're not seeing. The only problem with this is that it's difficult to test, so we don't have a whole lot of observational constraints on that. But it is one theory among many theories.
Hi, I have a two-part question. First part is, if dark matter is a scaffolding or a superstructure for ordinary matter, what would dark energy be? Would that form the same function, and in relationship to what? And the second part is dark energy evenly distributed throughout the cosmos, or is it clumpy in the same way that dark matter is?
It's a good question, and I think that's one of the few things that we think that we have some indication that we're actually seeing a very uniformly spread dark energy as far as we can tell at this point, but it's one of the ones that we want to keep looking into in more detail. If so, what you're seeing is, in terms of that scaffolding question, you're seeing that the dark matter is providing the scaffolding which things start to try to clump towards, but it's like running down an up escalator as the universe is being pulled apart by the increasing expansion rate due to the dark energy. So if you don't get to clump early enough, you'll never get to clump in a dark energy dominated model. And we're in fact lucky that there was such a long period in which the dark matter was winning. If Lexi hadn't won for the first half of the universe, we wouldn't be here today because we wouldn't have clumped to get here.
We're going to have one last question up here.
Is it possible to have two galaxies combined?
It is, and two galaxies actually do collide sometimes, and that's how we think we form massive galaxies. And there are people out here that study that up on the upper balcony again. But it's fairly rare because in a cluster of galaxies, for example, the distance between each galaxy is quite large. So usually they would just zip around and spin around without ever hitting each other. But because there's a huge amount of dark matter, they're all attracted to the center, and eventually they collide. And we have beautiful images of colliding galaxies where you see giant tidal tails coming up, and they certainly do. It's a really interesting process to study.
And we should warn you that our nearest galaxy, neighbor galaxy, if you look in the Andromeda constellation, the Andromeda galaxy, we are going to hit it. It'll be a little while.
Ladies and gentlemen, we do have to stop. Unfortunately, time is drawing nigh. I want to greatly appreciate your attendance here, and please let's give a warm round of applause to our presenters.